Um, I'm sorry about this morning. Um, I didn't expect to do a live stream, but I'm a little under the weather. So I'm doing a mic check, and it seems to be operating okay. To do a live stream, but I'm a little under. So sounds to me like the audio is doing fine. So I will start it in a minute. The weather. So I'm doing a mic. All right, I'm trying to test it here. Is it working? I'm not sure it's working. Okay, are we working? I'm not sure the audio is working. I'm not hearing anything. Oh. All right, I do hear it now. All right, so I'm probably not going to go too far today because of being under the weather a little bit, but let's do just the curvilinear motion. So in curvilinear motion, it's basically a situation where all right, the audio over here is so we started with this concept of a position, and we moved to a velocity being the derivative of the position. And essentially you're listing them in XYZ coordinates. It doesn't become immediately apparent of what's happening until you get to this section. It's the motion of the projectile. And this plot right here is an interesting plot because it's showing that if, and this is actually true, if you dropped a ball and you push this out here to the right at a certain initial velocity, then essentially what you would see is they would fall in the y direction at the same rate. So a snapshot shows that this one's just simply moving to the right while falling at the same rate. So here, so this one's falling at the same rate as that one. So you'll see this like a strobe that is happening like this. But what you notice here is the delta between these particular points is the same. So that's not too surprising when you go to consider, and we'll talk about that in a second, that the initial velocity, or the velocity in the x direction at any time t, is equal to the velocity in the x direction at the initial time. So in other words, there is probably another line that he could put here. Sorry, it's not a straight line, but it would be the same delta apart. So all of those are the same. Now, if you go down to this, what you realize is you have motion that occurs under a constant acceleration, meaning the acceleration in the y is equal to minus g here. What you find out is the acceleration in the x is equal to 0. And so if you develop the equations off of this, what you have now, what he's writing here is the general set here. And then he says, hey, wait a minute. Horizontal motion, or motion in the x direction, vertical motion, or motion in the y direction, you have no acceleration. Therefore, that goes away, this goes away, and this goes away. So, since that's the case, you can rewrite this equation right here, and you can rewrite this equation right here, And what he's doing here is he's taking the squared off and saying, hey, I'll just rewrite this equation there, which is essentially the same thing as that equation. In the y direction, you have an acceleration equaling to minus g. So what you do is you go in and you insert the minus g here, the minus g here, and the minus g here. And that's exactly what you get over here. You get this, the minus g. The minus g gets stuck right here, and the minus g, remember this is a plus, so that it becomes minus right there. Staring at these equations real quick, you'll notice something pretty interesting. The first thing you'll notice is, yeah, in fact, that is the case. The velocity is constant across this. In other words, let me change pens here. In other words, the distance between any one of these is exactly the same, meaning if this took place such that it was a strobe where there was a constant flash at a delta t, then you would see the movement such that this moved the same distance in each strobe. So it's as if on the right here, the ball is just moving to the right at a constant speed. And what you notice is the distance here is shorter or smaller than the distance down here. So the distance that happens here, the delta y grows, and y is, if you get down here, as time goes, I'm sorry, I meant to point to this one. As time goes, you'll have a quadratic effect, meaning you move a time and then a delta time more, you've got that squared effect, which makes it increase. You've done these problems before in physics, not a big deal. But let's go back and look at them, and we'll look at what to expect here that's different than what you had before. And I'll do it by just picking one of the problems. First, I'll pick the problem that behaves that way. There's a golfer somewhere, I think. Well, maybe there's not. Give me a minute. There's a golfer. Oh, good. It's 45 degrees. So let's just do this problem real quick, because this shows out to be one of the major differences here. Now, I don't remember what he's asking. So, okay, determine the speed at which it strikes the ground and the time of flight. Oh, and the distance the ball will land. So let's do all that. So we'll do all this, but we'll do it over here on this page. So it leaves at 80 feet per second. So again, x is equal to, well, yeah, vx naught times time. I guess I should have put, well, I could do this. Vx is equal to vx naught. Y is equal to, now, technically, let's do this. It's equal to y naught plus vy naught time minus gt squared over 2. And then vy is equal to vy naught minus g times t. So there's our set of equations. Brain freeze there for a second. Okay, so let's determine our coordinate system. So there's my X and there's my Y. So it's 45 degrees from the ground, but then you have an extra 10 degrees. So if you're looking at this, and the only reason you wouldn't put the coordinate system here, let me use a different ink. The reason you wouldn't put the coordinate system here is because then gravity would not be in the y direction. So you actually have to have your coordinate system such that the gravity is going in the opposite direction as y. So let's look at the Vx naught. This is 80 and this is 55. So you go ahead and let this come up. All right, it's there. Okay, so, and again, this problem is the only difference that you're going to see in what you've seen before. And I'll try to do my best at getting my way through this. So if you look at 80 times cosine degree of 55, that would pop out to 45.88. Oh yeah, we got to do word of the day. Okay, here. I should have done it earlier, but word of the day, I don't know, would be word. Okay. So I think I'm going to establish a standard that I go do it too. So this means that I need to log in here. So I'm going to do it a little bit better in the near future here. Okay, was it going to make me use that duo thing? Oh, not. Okay, so I guess I saved it. And this is dynamics. Go down to here. Go ahead and put you put yours, but there you go. Word of the day is word. Okay, so, all right, let me get rid of that. And okay, that was a response from the word of the day. Okay, so when you get a chance, put that in. I should give extra credit for watching the stream today since I'm supposed to be in the class, but again, I don't, anyway. So what we need to do now is find Vy naught, and it's, okay, so this was 80 times cosine 55. Hopefully, I put in 55. I think I did. Now, I got to put 80 sine of 55. And I have to put the D right here because this Octave MATLAB likes a D if I'm going to put in degrees. Okay, 65.53. Does that make sense? Well, if it was 45, they would both equal. If it's greater than 45, then this one would be larger than this one. In fact, it is. So that makes sense. So now I have an equation that looks like this. Now, the funny thing in the room is this. Or, I'll make it that color. So that term, the x naught, here, put it to you like this. The x naught and the y naught have to do with where you put the ruler at. For example, if I'm taking it like this little part right here is the origin. So if I put the origin where the guy hit the ball from, then I have x naught equal to 0. If I take the ruler and put the y from where the guy hit the ball from, then I have y naught is equal to 0. If I'm foolish enough to put the ruler somewhere else, essentially saying I'm going to use a coordinate system that's back here. Now, I've drawn this one right here. So this is what a smart person would do. This is what a stupid person would do. Why make this not equal to 0, like x0 equal to 5 foot, and then y0 equal to 10 foot, and that gives you something more you got to put in your equations. So now, I'll say this, though. There are times in which it's difficult to decide where you need to put it, and I'll work a problem like that in a second. So if I do that, and place the ruler at the location so that x naught equal to y naught equals 0, really meaning the origin is where the ball started from. Then what I've got is I've got this set of equations, x equal to, and I'm just going to go ahead and put the values in there. I don't have x naught, so I'll go ahead and do that. 0 plus vx0 should be 45.886x. And then I'll say y is equal to y0 plus 65.53. I'm grabbing this equation right here and sticking down here. By the way, that's not x, that's t. 65.53 times t minus, now my g, since he's decided to use this system, my g is 32.2 or 174 feet per second squared. If I was in SI, it'd be 9.81 meters per second squared, but I'm not there. So, I'll put it in here, and I'll still keep the 2 t squared. So, in essence, what I have here is a set of parametric equations, meaning that x is a function of time and y is a function of time. Meaning I can just move time around, move it forward or backwards, and it changes the x. That looks like a G. That's supposed to be a Y. And it changes the Y. So moving time around, I can change x and y. However, maybe I want them to look different. So if I look at this and say 45.886t, maybe what I should do is remove the parametric nature of this and take this t and stick it right in here and stick it right in there. You'll have to be patient with me for a minute. 65.53. Now what I'm doing is I'm grabbing this and I'm going to put in x over 45.886, and then I'm going to go over here and put in 32.2 over 2 times t squared. So the t, instead of the t, I'm going to put x over 45.886 squared. Get rid of all these arrows everywhere. And now, instead of a parametric set of equations, I have y as a function of x. Now, why is that beneficial for me? Well, because now, if I were to just say copy that picture and redrop it right here, and maybe make it a little bit bigger, or it really doesn't matter. What I'm actually doing is quite straightforward. I have x and y. I have a parabola, and I have a straight line. And now what do I have? Take the, come on, man. I'm trying to get the, okay. Get the golfing dude off there. Okay. I'm trying to get rid of the background. There we go. So it looks to me like all I'm doing is finding the points of contact, or points where these two are intersecting, a line and a parabola. So all you got to do now is find the equation of the line. Well, y is equal to ax plus b, or if you feel uncomfortable about a and a b, you could say c1 and c2, where these are two constants. First of all, the golfer started right here. So if I put in x equals 0, I'm supposed to get y is equal to 0, meaning this has to be 0. So what's the slope of the line? Well, the slope of the line is the rise over the run. And I don't know right offhand what it is, but he has told me that it is 10 degrees. So the rise over the run, I don't know what the tangent of 10 degrees is. But it's probably not that large. 0.17633, and there are more digits in MATLAB actually. If you just, I don't want to, if you do format long and then you go back, you get a whole bunch of things. So then it's like a whole lot of digits, but okay, I guess, if it's long, I guess it's short. Yeah, so the format's short. You also have a format bank if you only want 2 digits, meaning, excuse me, you go down to the penny, but we're not. We're not doing that. So here's your equation. I'm going to grab this. I'm going to grab that and make the equation. 17633x. So now if I want to know where these two cross, it's a pretty simple process. I just equate them. So I take 65.53x over 45.886, and I could have done this a little bit better. 32.2 over 2 x squared over 45.886 squared, and that is this equation. Then I take this equation and say, okay, 0.17633x. Now, I have an equation. Turns out it is a parabolic equation, and it's kind of a mess. But what I'll do is I'll go ahead and solve this. I grab that one and that one, put them together because they have the coefficient of x in front of them. And I'll say, good grief, 65.53 over 45.886 x. The x is already out. And minus, because I'm going to bring this one over here, 0.17633 and extra digits, minus 32.2 over 2 over 45.886 squared times x squared equals 0. Now, the first thing, without going too far, is I realize if I put in x equals 0 here and here, the equation is exactly satisfied. So I can go in and do this root 1, 2 is equal to minus b over plus minus square root b squared minus 4ac 2b, or I can just notice that, hey, wait a minute, I don't even have to do that, because now I can reduce it down one more step, 65.53, 45.886. And I might as well, let me take a minute and just figure out what each one of these numbers are. So this number, and then I'm going to copy this number down. And give me a second here. If I can move this to the bottom of the screen, I might be able to see it at the same time. So the first one, 65.53 divided by 45. Did I put in 46? 45.886 minus 0.17633. 1.2518. 1.2518. And I'll go ahead and leave the x in there, minus the other one, x squared. Okay. Shoot here. All right, the other one is 32.2 divided by 2 divided by 2 divided by 45.886 squared. Ooh, pretty tiny. Oh, did I do that right? We'll be able to check in a second. I'll show you how to check. 0.007 6465. Okay, so now, and equals 0. So now, of course, out of this, I get x equal to 0 is one root. Then I can just do this, and I can say x equals to 2518, because I can move this to the other side. It became a minus, so I take my minus number here, 0076465. X equal to, okay, so I should be able to, well, let's see if I can do it like this. Well, I'll go 2 back, and I'll call this A equal to And then I'll go 2 back. I'll call this B equal to, and then I can do A divided by B. 163.7. 163.7. Let's see if I'm correct. First thing I'll do is I'll go in. I'm going to go back to the original equation, which sits right here. And let me make it bigger so I can put it at the bottom of the screen so I can go in and grab this. And what I'll do is I'll say x equal to 0. And since it's a large enough number, I think it was, okay, it was less than 180. Okay, it was 163. And then what I'm doing is I'm setting a set here. And then I'm going to say y is equal to, and I'm going to do this, 65.53. I would say, let's see, I could say, if I've made a mistake, y'all could enter it in the chat. But if I did that, I need to be able to look at the chat. Okay, where do you look at the chat? Okay. Yeah, so that's, you're right. That's what I'm about to do right here. So what I'm doing is I'm going to do that to check myself. So, and if I've made a mistake, I guess I need to open another screen so I can see it, the chat, as I'm going through here. Let me run back to, first I'll go back to here, then I'll go back to here. I'm going to plot them and I'm going to find out, but I wanted to find them digit wise. So I'm trying to do this every way I can. Times x minus 32.2 divided by 2. And I'll go ahead and do this. Well, I'll go ahead and first I'll divide by 45.886 squared times x, and you have to put a period, asterisk, and squared. I'm going to put this at the end so it doesn't, if I don't, it just produces a bunch of numbers. And this way it doesn't. So now I can do a plot, x comma y, and I can check myself. Ooh. This is not a fast computer. Now, the next thing I need to do, there is a thing in here called hold on, which will hold the data on the plot so that now I can put another plot on there. So I'll do y line is equal to, and I have already forgot, you know what, I already forgot the slope, but I do know it's tangent degree of 10 degrees. Oops. Times x, and again, I'll put that there. Now do a plot. Now since I did the hold on, x, y, I think I did L for line. Now, got to go find it because, there we go. Now, okay, it does here too. There's this plus Z, a zoom in. So I can do this. And I think you can just keep going to the point where the digits keep. So what you're seeing down here, 163.704, 163.704. They all say that. I've zoomed in so close that 163.704, is that what I got? Yeah, so that's what we ended up with. Now the next question he asked, I think he asked, how long did it stay in the air? I believe. I may be incorrect about that. Okay, he wants to know the distance when it landed, the speed at which it strikes the ground. He wasn't interested in how long it ended up staying in the air, but I think we have to find that if we're going to find the rest of it. So, in other words, let's put it to you like this. I know that eventually, okay, what was it? X was 163.7. So if I stick in t into this equation, 163.7 over 45.886 tells me that my time was, I don't know why I did that, but okay, I've got two different, okay, there we go. One, okay, I'm on the wrong screen. There, now I'll do that. Okay, 163.7 divided by 45.886, 3.56, yeah, 3.57, yeah, I'll go ahead and carry the other digits, 675. That's how long it took to reach there. Now, if you wanted to know the velocity, now, the velocity in the x direction never really changes. So in other words, you take a snapshot of the ball, and here's what you might see. Let's see if I can go down. It's kind of interesting if you think this way, and that is that if you put a strobe on this, what you would get is you would see this. I'm trying to make these all the same distance apart. In other words, the strobe would show that the delta x, if the strobe was constant, it would show the delta x this way. But what you're finding out here, so in other words, the Vx naught is equal to a constant. But if you look at this, when you get to the very top of the thing, where the what do you call it, the apex, or the very highest level that the ball went, it pretty much slows down to 0 and then returns back to the point where, you know, the velocity when it hits the ground is much larger than at the apex. Now, it turns out that if this ball hit back over here and it was actually at the same location, then the velocity hitting the ground would be the same as the velocity leaving out up here. But this is not the case for this. All you got to do is you got to go over here and say, let me zoom in. You just go over here and say, well, Vx is equal to Vx naught, and Vy is equal to Vy naught minus G times T. Now, I'll have to remember what Vx naught was. 45.886. Vy was the 65.53. Okay. Here, to make it so that I can write legibly. And then G was 32.2. Now, all you do is you return in here and put this, and you have Vx still 45.886, and Vy becomes something other than what it was, which is here. $65.53 minus 32 point, whoops, 2 times the number of seconds, which was missing. oh, here it is, 3.56. Oh, it was right above me, 3.5675. Minus 49.34. Okay, wait. Minus 49.34. That makes sense. The velocity should be going down. So right now it's going down and to the right. Now, I would expect it to be going slightly less than the initial 80. If it went down to right here, this is the point at which it's going 80, where the elevation is exactly the same. I'm sorry. So here, let me rephrase that. So if I took a perfectly horizontal line where this crosses, this is 80 when it hits right here. Up here is the slowest velocity. It's only that component. As it's going, it's increasing. So it should be slightly less than 80. And so the question is, what is it? It's 45.886 squared plus 49.344 squared, and the square root of that becomes squared plus 49.344 squared, and I did do a square root, 67, so it's about 67.3, so it's slightly less than the magnitude of the velocity is about 67, slightly less than the 80, but just like what you know, as it goes further and further and further, it goes faster and faster and faster. And if you wanted to, you could go in and say, I mean, this is kind of silly, but this is what you did last time, in which you went in and you said, okay, well, I don't want to get too distracting here, but I think that's the point. That's the problem. So what did we just do? Here's the key. We didn't do that much more than what you did in physics. In physics, they would have a parabolic motion. They might ask you how far downfield it went. They might ask you how high it went. They might ask you the velocity at the top. And so what you find out is all these x velocities are all the same length, but the y's are not. They start changing. The y's are dictated by the gravity, the appearance of the gravity, because you had this. Now this t squared and this gravity was making the ball go up and then come back down. So you might do things like that. Well, all that you're doing here, in addition to what you've done back then, is they may phase the problem in such a manner that maybe you're looking for where it might intercept here. So they'll maybe give you a straight line. In the book, there are cases in which, and let's just look at them. Here's a case where they were annoyingly giving you this. So what do? You go in and you set x as a y as a function of x. Means you have your parabolic. So there's your parabolic. So all you're doing is finding out where this parabolic function, that doesn't look like a parabolic, but anyway, where this parabolic function matches or crosses this one. There is a couple of cases where, in cases like this, there's not even that. It's basically, that it's 10 and 3, the basketball's got to be right there. You know the x equals 10, y equals 3. That's exactly where you are. Now, the other thing too is on this, if you want your coordinate system to go right here, then this ball is at x equal to 10 and y is equal to 1. And that's, you know that. Other things like this, let's see, there's another one where it may be down below me. Here. Okay. This is a good one, but it's kind of strange, but we'll do that one maybe. Okay, here's one where rise over run, you get your slope, you get your parabola. This is a little bit of a one in which the guy's hitting it and he has to find a constant velocity to get back there and get it. There, you're just going up and hitting the wall. Where is that other one? There was a good one about, there it is. There's a ski slope. Now, this one is a little bit strange because if you put your coordinate system here, your parabola ends up looking like so. But your straight line actually has a negative intercept. So this is y is equal to ax plus b, but b becomes minus 4, and the slope kicks down. The rise over the run is rise, run, so it's minus 0.75x minus 4. So this one has an intercept. And so that's the only difference here is you've got this one having a line crosses twice, not a big deal. So that's it. There's nothing more to this. There's, it's just different pictures, different things. Like here's a guy I guess he's gonna block the ball. Clearly hands attempted to block it. So he's attempting to block it. And so he's wanting to know if he's 5 foot out away from the thing, how high does he have to jump to stop it? If in fact he's pushing it. Now, he's telling you it's 30 degrees so you can get the Vx and the Vy, and you can track it over this, knowing that this is 7, this is h. So you could do the equation that you could find this distance and then add 7 to it to get the h. There's the golf guy. Here's catapulting, looks like water balloons against the building. So that's pretty much it. I think we have run to our time, so I'm going to go ahead and call it quits there. Again, I have to apologize about not making it today. I'm going to try to make it on Wednesday. I think I'll feel better. But we'll just do the best we can through all this. Okay. Trying to find there we go. I'm going to go ahead and stop the stream now. So I think it was right there. There's okay.